Last chapter, radioactivity. Now, we've previously studied the structure of an atom as composing of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons form the central nucleus. Negatively charged electrons orbit the nucleus. We also talked about the chemical reactions involving transfer of electrons or sharing of electrons to form what we call chemical bonds. In this chapter, we shall study reactions originating from the nucleus called nuclear reactions. First, let's look at stability of atoms. Now, a strong nuclear force holds the positive protons and the neutrons together in the nucleus and is what determines if a nucleus is stable. In a stable nucleus, the force is strong enough and brings enough energy to hold the nucleus together permanently. Most of the nuclei formed during the formation of the Earth nearly 14 billion years ago are still in existence today. But not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess protons or neutrons. This is called radioactive decay. Unstable nuclei are said to be radioactive and emit radiations. Isotopes that are radioactive are called radioisotopes. So, how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons. A radioisotope that lies to the right of the stability line has too many protons. Nuclear reactions are quite different from chemical reactions. They occur within the nucleus and involve protons and neutrons. They release an enormous amount of heat and are unaffected by environmental factors such as temperature, light, and so on. Radioactivity can be natural or artificial. Natural radioactivity occurs when nuclides split spontaneously in nature, yielding new particles and energy. Artificial radioactivity occurs when large, stable nuclides are bombarded with fast-moving, high-energy particles, causing instability, and the nuclide splits into smaller nuclides with emission of particles and energy. The British scientist Ernst Rutherford was one of the first to show that radioactivity could consist of three distinct types of radiations. The three differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed to a fluorescent screen which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into three components. One of these is deflected upwards by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays.
A part of the beam is deflected downwards, indicating that it is positively charged. These radioactive emissions are called alpha rays. Note that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiations. The portion of the original beam that is undeflected is due to radiations that is not charged and are called gamma rays. Penetration power. The three radioactive emissions have different penetration powers. Alpha particles are the weakest. They travel slowly through air and are stopped by a sheet of paper. Beta particles are stronger. They penetrate paper but are stopped by a piece of aluminum foil. Gamma rays have the highest penetration. They penetrate paper and aluminum foil and are only stopped by a thick lead block. So radioactivity is the spontaneous random emission of particles from the nucleus of an unstable nuclide. The process of radioactivity is not affected by such external factors as temperature, pressure, or chemical composition. When a nuclide emits the radiation, it is said to undergo radioactive decay. During radioactive decay, the nuclide will emit alpha or beta particles, and this may be accompanied by a release of energy in form of gamma radiations. Alpha decay. Alpha decay occurs when an unstable isotope gains stability by losing a whole nuclide. An alpha particle is basically a helium nucleus represented as shown here. So if a nuclide decays by release of an alpha particle, the mass number decreases by 4 and the atomic number by 2. So if a parent nuclide X with mass number A and atomic number Z undergoes an alpha decay, we shall have a daughter nuclide Y with mass number reduced by 4, that is A minus 4, and atomic number by 2, Z minus 2, plus an alpha particle which is essentially a helium nucleus. Notice that the daughter nuclide is completely different from the parent. To identify the daughter nuclide, we simply check the new atomic number from the periodic table. For example, polonium undergoes alpha decay to form lead as shown here. Now for an example. If uranium-238 undergoes a single alpha decay, what element will be formed? In the solution, we write the equation uranium-238 undergoing alpha decay. Mass number reduces by 4 to give 234. Atomic number reduces by 2 to get to 90. From the periodic table, that new atomic number 90 is thorium. Beta decay. An unstable nuclide may also gain stability by conversion of a neutron into a proton. Consequently, an electron is emitted. This is beta decay. So a beta particle is basically a high-speed electron resulting from the conversion of a neutron to a proton and is represented as shown here. And so if a nuclide undergoes beta decay, the mass number remains unchanged but the atomic number increases by 1. For example, radioactive sodium undergoes beta decay to become magnesium. Gamma rays are not particles, but rather are electromagnetic radiations that usually accompany the emission of alpha or beta particles. Some nuclides might be in an excited state, and to achieve stability, they may emit energy in form of gamma radiation without producing new isotopes. For example, cobalt-60 and thorium-230. Sometimes, a radioactive decay may result in a new nuclide, which is also unstable. The daughter nuclide will thus undergo another decay until a stable isotope is obtained. This is called a decay series. For instance, thorium-232 is unstable. It undergoes alpha decay to form radium-228. Radium-228 is also unstable and undergoes a beta decay to form actinium-228. Actinium-228 is unstable as well. It undergoes a beta decay to form thorium-228. Thorium-228 is also unstable. It undergoes an alpha decay to form radium-224. Radium-224 is also an unstable isotope. It undergoes yet another alpha decay to form radon-220. This decay series continues until we get a stable nuclide, lead-208. From this series, you notice that two similar particles can be released in succession to form a new nuclide. For instance, radium-228 undergoes two successive beta decays to form thorium-228. This equation can be summarized as shown on your screen. Thorium-228 undergoes two successive alpha decays to form radon-220. These can be written as shown on your screen. Half-life. The rate of decay of any radioactive material depends on the number of nuclides present. The time taken for half the number of nuclides initially present in a radioactive sample to decay is called its half-life. Consider 4 grams of radium whose half-life is 1,600 years. After 1,600 years, 2 grams will have decayed, so we shall have remained with 2 grams. After another 1,600 years, half of the 2 grams will decay, so we shall remain with 1 gram. Another 1,600 years, and half of 1 gram decays, so we remain with 0.5 grams, and so on and so on. This can also be given in form of percentage. Initial amount is always equal to 100%. Mathematically, if N0 is the original amount of a sample, N the number of half-lives, then the remaining amount N is given by N is equal to N0 times a half raised to N. For example, if we have 8 grams of radium whose half-life is 1,600 years, how much will be remaining after 6,400 years? Our formula N is equal to N0 times a half raised to N. First we calculate N, the number of half-lives. One half-life is 1,600 years, so 6,400 years is equal to 4 half-lives. That is simply 6,400 divided by 1,600. So N is equal to 8 into a half raised to 4. N is equal to 8 times 1 over 16, which is equal to 0.5 grams. This is the amount that will be remaining after 6,400 years. Now, this technique is used in radiocarbon dating using carbon-14 to estimate the age of fossils. For example, an excavated skull is found to have the activity of carbon-14 of 12.5%. If carbon-14 has a half-life of 5,600 years, find the age of the skull. This time we have our amount in percentage. Original activity or amount is equal to 100%, always. Final activity or amount is equal to 12.5% that we are given. Half-life is equal to 5,600 years. So what we need is the number of half-lives. Once we get it, because one half-life is 5,600 years, all we will need to do is multiply to get the age. So n is equal to n naught times a half raised to n. 12.5 is equal to 100 times a half raised to n. We divide both sides by 100, so we shall have 0.125 is equal to a half raised to n. I love to work with decimals, so a half is the same as 0.5. So we have 0.5 raised to n is equal to 0.125. Put your best mathematics. Introduce logs. N log 0.5 is equal to log 0.125. To remain with n, we divide both sides by log 0.5. If we do that, n is equal to 16. So there are 16 half-lives. Each half-life is 5,600 years. So how many years are those in total? We simply multiply, and if we do that, we get 89,600 years. That is the age of the skull. A German scientist, Otto Hahn, discovered that breaking up the nucleus of uranium-235 into two parts emits 200 million times the energy of the neutron which triggered it. A process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amount of energy, is called nuclear fission. When the nucleus of uranium-235 is bombarded with neutrons, it absorbs one of the neutrons, thus forming a highly unstable compound nucleus, uranium-236. This is what triggers the nuclear reaction. During the process of fission, uranium-236 splits into two product nuclei, which are barium-141 and krypton-92. The unstable uranium-236 nucleus also releases 3 neutrons in the process. The nuclear equation for the reaction is shown here. These neutrons can be absorbed by other uranium-235 nuclei, resulting in a chain reaction. This leads to exponentially high amount of energy being released by a single reaction. Nuclear fusion. Nuclear fusion is a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amount of energy.
Next, we look at the applications of radioactivity. First, use of radiations in radiotherapy. Gamma radiations can be used in radiotherapy for the treatment of cancer. These radiations are directed on the area of the body that is affected by cancer. At high doses, radiation kills cancer cells or slows down their growth by damaging their DNA. The dead cancer cells are then broken down and removed by the body. Radiotherapy doesn't, however, work straight away. The cancer cells can take up to a few months to die and be removed by the body. Radiotherapy can also be used to destroy other tissues of the body that are not useful. For example, radiotherapy is often used for the treatment of overactive thyroid glands. If the thyroid gland produces too much thyroxine hormone, it can result in heart palpitations, anxiety, fatigue, and mood swings, amongst other symptoms. Radiotherapy can be used to destroy some cells of the thyroid gland and thereby reduce the amount of thyroxine hormone produced. Secondly, use of radiation as tracers. Beta and gamma radiations can also be used as tracers. Tracers in the body can provide useful alternatives to surgery. A small amount of a radioactive material is introduced into the body, and the radiographer follows the passage of these materials through the body using specialized equipment. Beta and gamma sources are used because they pass out of the body and can therefore be detected. Remember, alpha particles cannot travel through anything thicker than a sheet of paper. Barium meals and barium enamels are common examples of radiations used this way. The radioactive tracers are used to detect possible blockages. Radioactive tracers are also used to find leaks in water pipes. For medical tracers, isotopes that have very short half-lives are selected. The half-life is long enough that they stay active for detection to be done, but short enough that they reduce the dose level as quickly as possible. Thirdly, use of radiations in smoke detectors. Stream detectors emit a constant stream of alpha particles. A sensor continuously detects these particles, causing a small current. If smoke particles come between the source and the detector, current is decreased and an alarm goes off. Fourthly, use of radiations in sterilization. Gamma radiations are used to sterilize hospital equipment and are also used to kill bacteria, mold, and insects from food before the food is packaged. This increases the shelf life of the food. The food is safe to eat and doesn't become radioactive itself, as it is irradiation rather than contamination. Finally, dangers of radioactivity. Now, nuclear power stations provide electricity, which is of course extremely useful. However, they also make radioactive waste. Radioactive waste can come from a range of activities, including generating electricity from nuclear power stations, treating medical illnesses, and conducting research. Radioactive waste can be harmful either through irradiation or contamination. Irradiation is when a person or an object is exposed to radiations without coming in direct contact with the radioactive source. The person doesn't make any contact with the radioactive barrel, but since radiation can happen at any distance, the person is still at risk. The damage to the person only happens when the person is in the area of the radioactive waste. Therefore, the person is only exposed to the radiations for a short time and so receives a low dose of radiation. Contamination is when a person actually comes in contact with the radioactive waste. The person takes the radioactive source with them and so is exposed for a longer period of time and consequently has a higher dose which can lead to more damage. Contamination can happen through a number of ways: touching, breathing, or ingesting. Background radiations come from artificial or natural sources around us that we experience daily. It is low in magnitude, so it isn't harmful. However, for some radioactive waste to reach this low background level, it may take several thousand years. How harmful a radioactive waste is depends on the half-life and whether a person is irradiated or contaminated.